All right, inequalities. One thing to keep in mind with an inequality is that, okay, if 2 is less than 9, that's true, but what can we do to both sides of this inequality? Well, we can multiply by 3, for example. That's fine. We could divide by 3. We could subtract to both sides. We could add to both sides. Okay, you can try all those things and they work. But what's the one thing you have to be careful of? Well, what happens if we multiply by -1? Well, then we have that -6 is less than -27. Is that true? Look on a number line. It's not true. So remember that if you multiply or divide by a negative, you need to switch the inequality sign. So that goes for inequalities of a simple form, such as 3x minus 5 is less than 7. Okay, so we're allowed to add 5 to both sides. We get 3x less than 12. We can also divide by both sides, and that's fine. X's are less than 4. However, let's try another one where we have -2x plus 8 greater than or equal to 14. Subtract the 8, you get 6 and -2x. Okay, so now when you divide both sides by -2, you need to be careful of switching the sign so that x is actually less than or equal to -3. So that's a little bit of a review on how to solve inequalities in a similar fashion to solving equations. But as you expect, it does get a bit more complicated. So we could have compound inequalities. So for example, we might have 4x less than -8 and 1 minus 2x greater than -5. What does the and mean? Well, and tells us that this is sort of like an intersection of solutions. So we want the solutions from this and this intersected. So what is common between the two? Well, let's solve them first and see. So divide by 4. We're allowed to do that. Doesn't change the sign. So x is less than -2. Let's just visualize that. There's -2. Everything less than that is part of this inequality. What do we get here? Well, if we subtract 1 from both sides, we get -2x greater than -6. Divide by a negative. Careful. So when you divide by the negative, you're going to switch the inequality so it's x is less than 3. All right, so you have 3. X's are less than 3, not including 3. So now what is the intersection of these two inequalities? Well, the common part is actually the less than -2, because that part is common. So the resulting answer would be x less than -2. Or you could write the set of all x's such that x's are less than -2. Now what if you had a statement similar to this, but it said or? So x plus 3 less than 7 or 2x greater than 12. Subtract 3 from both sides. On this end, you get x less than 4 or divide by 2, x greater than 6. Now what does the or imply? Well, or implies a union. A union will include all possible solutions from both sets. It's very welcoming in that sense. So x is less than 4 are included, as well as x is greater than 6. So we would include both. You could write this as the set of x's such that x's are less than 4 or x's are greater than 6. If you wanted to write that in interval notation, you could write this as negative infinity to 4, open bracket, union 6 to infinity. Likewise, this one over here could have also been negative infinity to negative 2, open bracket. Remember, it's a square bracket if it includes the point. Okay, now what if we had absolute value inequalities? So here's an example. Let's say you had absolute value 3x minus 2, absolute value less than or equal to 4. One thing to consider before we get there is absolute value inequalities. Let's take a simpler example. What if you had absolute value of x less than or equal to 5 versus absolute value of x greater than or equal to 5? So let's consider those before we get to solving this example. So what numbers could you have so that the absolute value is less than or equal to 5? Well, you could try some numbers in there, but we could also look at the number line. Well, when is it equal to 5? Either at 5 or negative 5, when you plug that in, it's equal to 5. When is it less than? Well, less than will be if the number value itself, the net value, is less than 5. It can't be a 6 because then it wouldn't be less than 5. And it can't be a negative 6 because the absolute value would be less than 5. So all of those points together would be everything in between negative 5 and 5. So notice that the less than symbol would split this absolute value inequality into two statements. It would be saying that x is less than or equal to 5 and intersection x is greater than or equal to negative 5. Another way of stating that is that x is between negative 5 and 5. This is actually an and statement. I prefer writing it this way. Now, what's the opposite statement to that? Well, same thing here. We have our equals. 5 and negative 5 make it equal to 5. But when is it greater? So all of this outside is when making it greater. So 6, for example, you can plug in a negative 6 and you can prove yourself that this is a representation of that. So how do we write that? Well, if it's greater than or equal to, we would split it as either x is less than or equal to negative 5 or x is greater than or equal to 5. So we've got greater than is going to give us the outskirts and less than is going to give us the inside. This is important because when we see an inequality to solve, we want to know how we split it. In this case, we have a less than. So the absolute value is on its own. If it wasn't, then you would solve it to be on its own. But now if it's less than, that means that this is between negative 4 and 4. This 3x minus 2 is between those numbers. This is also an and statement of greater than or equal to negative 4 and less than or equal to 4. So to solve this, you could add 2 to all sides. And then divide by 3 to all sides. So you can see that x is between negative 2/3 and 2, including both. So we could write that in interval notation as this. What if we had greater than? So you could think of, say, 2x plus 5 greater than 3. So now how do we split that? Well, it's greater than, so we have an or statement of the outside part. So either 2x plus 5 is less than negative 3 or 2x plus 5 is greater than 3. So you've got your outside parts. So now you can solve, and it's an or statement. 2x subtract the 5, negative 8. So then when you divide, you have negative 4. Or subtract the 5, you get negative 2. Divide, you'll get greater than negative 1. So if you map that out, you'll see that it's less than negative 4 and greater than negative 1. So all the way from negative infinity to negative 4, or all the way from negative 1 to infinity, including everything. So knowing how to split based on the sign that you get is really important. And also make sure to isolate your absolute value first. Now, what if we had a polynomial inequality? So say you had x squared minus 2x minus 15 greater than 0. Well, think about what this is. Visually, this is sort of like some sort of parabola, and we're seeing when is it greater than or equal to 0. And if it was like this, then it would be in these parts right here. But we're not sure. It all depends on, hey, where does it cross the 0? So it's very similar to solving an equals 0 case to begin with. But then we have to explore what happens in each interval. So we can find where it equals 0, but those are the points at which it crosses from being positive to being negative. So let's see. In this case, we're looking for it to factor to be able to see where it equals 0. So does this factor? Yes, it does. So x minus 5 plus 3 will give you multiplies to negative 15, and negative 5 plus 3 is negative 2. So keep that as a greater than or equal to. So we factor, and now we can say that at at 5 and at negative 3, we have crossing points. So let's explore what happens at those points. I'm going to use open circles because it's greater than and not equal to. So let's explore what happens in this case. Well, you could just pick a point in each region. This region's up to negative 3, between 3 and negative 3 and 5, and above 5. We can also test the factors themselves, like if x minus 5 is positive and x plus 3 is positive, then we know the whole thing's positive. So in this region here, under negative 3, is x minus 5 positive or negative? Well, let's pick a point, let's say negative 4. Negative 4 minus 5 is going to be negative 9. So yes, that one is negative. But then, what happens if we add 3? Negative 5 plus 3, for example. I'm just picking a random point in here in this interval. So negative 5 plus 3 would be negative 2, still negative. So those two negatives give you an overall positive. So that implies that the parabola is going like this, and it is crossing here because that's a point at which it would equal 0. So it's likely that this will be negative and positive, but let's check. A point in between here is 0, so 0 minus 5 would be negative. 0 plus 3 would be positive. Yes, that's negative. A point greater would be 6, for example. 6 minus 5 is 1. 6 plus 3 is also, and they're both positive. So we can see that this implies that up to negative 3 we have a positive, as well as past 5, but negative answers exist in between negative 3 and 5. So now let's look back at the question. The question was asking, when is this greater than 0? Well, that means when is it positive? So it's positive all the way from negative infinity to negative 3, as well as from 5 to infinity. Let's try another example. So let's say you had x cubed plus x squared minus 16x minus 16 less than 0. Again, we're looking for what are the points at which it would equal 0, which we can find by factoring, and then looking at the regions in between those points to see when it is less than 0. So let's try to factor this. I'm going to try grouping here. So x squared comes out, x plus 1. Negative 16 comes out, x plus 1. So x plus 1 is a common factor, x squared minus 16 is left, and that's a difference of squares that we can see is x minus 4, x plus 4. So to figure that out, we have our critical points here of -1, 4, and -4. So let's place those on the number line. And again, these are all open circles, -1, 4, and -4. So now we want to test these regions and see what's happening. Notice that now it's a cubic. A cubic looks a little different than a parabola. A cubic would usually have one bend of some sort like this. So it still goes between, say, positive, negative, but it might be the other way around as well. All right, let's say we have something in here. We can test that region. So -5, what happens to this term? -5 plus 1 is still negative, so that's negative. -5 minus 4 is negative, and -5 plus 4 is still negative. 3 negatives give us a negative overall. So actually, it probably looks more like this. Negative, positive, negative, positive. Usually it follows a pattern like this unless you have a double root. So for example, if these 2 points were actually coming from, let's say, x plus 2 squared, that would mean that x was -2 twice. So then instead of looking like that, it would bounce at -2. And so then it's still positive. So be careful of that case and don't assume it's always alternating. All right, so let's try another point, -3. -3 plus 1, negative. -3 minus 4, negative. -3 plus 4, positive. So that becomes positive. And same here, you can do the same and fill in the rest of the table and you'll see that. So that would be between -infinity and -4, or between -1 and 4. Finally, let's take a look at rational inequalities. This means that we have a fraction. So 5x minus 9, x minus 5, for example, less than or equal to 3. Now with rational inequalities, we have a little bit more going on. Rational equations have many points. You could try to put this into a graphing calculator and see that it's quite wavy. But one thing that we still need is we still need to have 0 here. So for the previous question as well, for the polynomials, you always want to have 0 on one side. Same goes with rational inequalities. So let's move that over. So we have 5x minus 9 over x minus 5 minus 3 less than or equal to 0. We need that 0 because the 0 gives us some properties. It gives us the property that if the numerator is equal to 0, we have potential crossing points of our function. So we really want to find those crossing points so that we can then test the regions accurately. But the other thing we also have is we have a denominator here. So we want to be really careful of that denominator because we know that x can never be negative. It can never give us the 0. We also know that x could never be 5 because 5 minus 5 gives us 0. So be really careful of those denominator points as well. So when we find our critical points to test our regions, we want to consider both the numerator and the denominator. But before that, we need a common denominator. So that gives us 5x minus 9 minus 3x, multiply it out, plus 15, all over x minus 5. So we combine that, 5 minus 3 is 2x. Negative 9 plus 15 is going to be plus 6, all over x minus 5. So now we can consider the critical points, which come from both the numerator and the denominator. The ones that come from the numerator will follow this inequality in terms of being equal or not equal, but the one in the denominator can never be equal. So we know that x cannot ever be equal to 5, but we also know that it passes through 0 when x is negative 3. That comes from the 2x plus 6 being 0. And if you solve that, you get the negative 3. So our critical points then, we have an open circle at 5 and a closed circle, because it can be equal there, of negative 3. Now you would test the regions and see what happens. It may be easier to actually factor this 2 out, just so you see that the 2 doesn't really matter. It could be divided out, but the x plus 3 and the x minus 5 really matter there. So negative 4 plus 3, and we do the same thing to test positive and negative. Negative 4 plus 3 is still negative. Negative 4 minus 5 is negative, so that's a positive. I'll pick a 0 in between there, so 0 plus 3 will be plus. 0 minus 5 is minus. And I'll pick a 6 here, so 6 plus 3 is 9. And 6 minus 5 is still positive. So positive and negative. And now the question is, when is it negative? So the answer would then be from negative 3 all the way to 5. Now let's consider one more case, and that's if you had an inequality that as you simplified, you ended up with something factored like this: x minus 3, x minus 5 over x minus, or plus 2, let's say, greater than or equal to 0. So you could have had to do quite a bit of work to get here, but the goal is to have a 0 here and everything as factored as possible. That way you know where you can't have a denominator, and also what your potential crossing points are. Be careful of not multiplying both sides through by the denominator, because then you're losing your original restriction of what could not be here in the denominator, in this case a negative 2. So we know that x cannot equal negative 2, and at x is 3 and at x is 5, we have critical points, potential crossing points. So again, we want to test our regions and see, when is it going to be greater than or equal to 0? So negative 2 cannot have that. 3, we could have that. And 5, we could have that. So again, let's test the regions with the factors just to see where is it positive and where is it negative. And so we can see that between negative 2 and 3, it's greater than or equal to 0, and greater than 5, it's also greater than or equal to 0. So that means negative 2 to 3, or 5 to infinity.